In Proton NMR, splitting tells us how many neighboring hydrogens are next door. Integration answers a different question. How many hydrogens are responsible for each signal? Today, we focus on integration, which tells us the relative number of hydrogens in each environment. Integration measures the area under each signal. A larger area means more hydrogens are responsible for that signal. In other words, area is directly proportional to the number of hydrogen. If a signal is split into a triplet or quartet, the whole multiplet belongs to the same hydrogen environment. Whole multiplet equals one signal area. You usually do not need to estimate the area by eye. Your job is to read the integration, then interpret the ratio correctly. Integration usually gives a ratio first. Sometimes this directly gives the number of hydrogens. Other times, we scale it using the molecular formula. So, ratio first, exact number later. Bromoethane CH₃CH₂Br has two proton environments. The CH3 group contains 3 hydrogens, while the CH₂Br group contains 2 hydrogens. In the spectrum, the CH3 signal integrates to 3 hydrogens, while the CH₂Br signal integrates to 2 hydrogens. So, the integration ratio is 3:2. The CH3 signal integrates to 3 hydrogens. So, the 3 hydrogen caused the signal. But it appears as a triplet because there are 2 neighboring hydrogens on the adjacent CH2 group. Hence, 2 neighboring hydrogens cause the triplet because of the n+1 rule. 2 + 1 = 3, it gives a triplet. Butanone CH₃COCH₂CH₃ has 3 proton environments. The CH₃CO has 3 hydrogens. The CH2 has 2 hydrogens. And the terminal CH3 has 3 hydrogens. In butanone, the integration ratio is 3:2:3. The 2 CH3 groups each integrate to 3 hydrogens, while the CH2 group integrates to 2. 2 signals can have the same integration ratio, 3 hydrogen, 3 hydrogen, but still be different environments. In butanone, both CH3 groups integrate to 3 hydrogens, but they are not equivalent. Therefore, same integration does not mean the same signal. In 1,3-dibromopropane BrCH2CH2CH2Br, the 2 N-CH2 groups are equivalent because the molecule is symmetrical. Together, they contribute 4 hydrogens. 4 hydrogens by the 2 N-CH2 groups and 2 hydrogens by the middle CH2 group. The 2 N-CH2 groups together integrate to 4 hydrogens, while the middle CH2 group integrates to 2 hydrogens. So the integration ratio is 4:2, which simplifies to 2:1. In this diagram, I am showing 4H and 2H to make the actual number of hydrogens clear. But in many spectra, the integration may be displayed as the simplified ratio 2:1 instead. Both mean the same thing. The NCH2 signal represents twice as many hydrogens as the middle CH2 signal. Equivalent groups combine into one signal. Equivalent groups can add together. That is why the two NCH2 groups appear as one environment with 4 hydrogens in total. If the ratio is simplified, use the total number of hydrogens from the molecular formula to scale it, meaning 1 plus 2 equals to 3 parts. 6 hydrogen divided by 3 parts equals to 2 hydrogen per part. Hence, the actual hydrogen is equals to 2 hydrogen is to 4 hydrogens. Quick check. A compound has 8 hydrogen atoms. Its proton NMR integration ratio is 3:1. How many hydrogen atoms are in each environment? The ratio has 4 parts. 8 divided by 4 equals to 2 hydrogen per part. So 3 parts is 6 hydrogen and 1 part is 2 hydrogen. Therefore, the answer is B. Integration tells us how many hydrogens are in that environment. Splitting tells us the number of neighboring hydrogens. Therefore, integration equals own hydrogen. Splitting equals neighboring hydrogens. In summary, integration gives the ratio of hydrogens in different environments. Integration equals hydrogen ratio, not the absolute number of hydrogens. If the ratio is simplified, use the molecular formula to scale it. In the next video, we will put chemical shift, integration, and splitting together to interpret a full proton NMR spectrum. If you want to learn more about A-level chemistry, be sure to subscribe to this channel, and I'll see you in the next one.